All right, it's my pleasure to introduce Michael Womack from UC Irvine, who will speak to us today about classification of steady gradient Ricci-Yang-Mills solitons on surfaces. So please, Michael.
Awesome. Thank you. And thank you for the invite for the presentation. So yeah, I will talk about this recent result for classifying the steady gradient Ricci-Yang-Mills solitons on surfaces. And to start, I'll talk about the context sort of with the generalized Ricci flow and solitons for the generalized Ricci flow briefly, and then sort of go to why we would consider the Ricci-Yang-Mills setting, and then kind of put some context for what the classification of Ricci solitons on surfaces is in like the classical setting, because I think that sort of makes this result um, more interesting just knowing the context. So to start, the generalized Ricci flow is we start with a oriented Riemannian manifold and then a closed three form on this manifold. And we have this geometric evolution equation that flows both the metric and the three form. And this is sort of the main points are this generalized Ricci flow is the gradient flow of a certain Schrodinger operator that has a Perelman type energy or entropy monotonicity formula. So a lot of the analytical theory sort of parallels with the Ricci flow, which you, I guess, would hope, given that it's supposed to be like an extension of the Ricci flow. Um, and then it's gauge equivalent to this pluriclosed flow that my advisor, Jeff Streets and Tian introduced in 2009. So the goal of this was to sort of extend the Ricci flow picture beyond so into complex geometry, you have the Kähler Ricci flow, but then you need to extend it to the non-Kähler setting. And in trying to do that, you end up considering, I think there's a variety of options, but one of these options is in particular this pluriclosed flow, which is very well adapted to studying the non-Kähler sort of Ricci flow picture. And then this generalized Ricci flow is the sort of analog that works well in the generalized geometry context. And then originally this was introduced in physics as the renormalization group flow. So it has physical origins, though we're not going to talk anything about that here. So we're kind of just um, in the math setting. So in studying any geometric flow, sort of the first step is understanding what the critical points of this geometric flow look like. And the diffeomorphism invariance of this flow leads you to considering solitons, because if you have a critical point, you can also just evolve it under some set of diffeomorphisms. And these diffeomorphisms are going to be generated by some vector field. And if this vector field is the gradient of a function, what we get is a gradient soliton. And if we consider the steady gradient generalized Ricci solitons for the generalized Ricci flow, they have to satisfy this set of equations where we still have this three form H, and then F is the potential function where grad F is like the vector field generating the diffeomorphism that this is evolving under. So um, a couple points to maybe just say about generalized Ricci solitons relative to the Ricci soliton picture is that um, generalized Ricci solitons, if you have a shrinking or expanding soliton, then using this entropy functional, you can actually show that the H has to be zero and it just reduces to a classical Ricci shrinking or expanding soliton. So the natural sort of thing to think about to study in the generalized Ricci flow picture is the steady solitons. And an interesting sort of feature of the generalized Ricci flow is you have these non-trivial compact steady gradient generalized Ricci solitons in dimensions greater than or equal to 3. So in the classical Ricci flow setting, any compact steady gradient Ricci soliton has to be trivial. So it's just flat, Ricci flat. And the existence of these non-trivial guys is kind of an interesting feature just for the generalized flow. So related to that is some recent history in trying to understand these generalized Ricci solitons. And I'll talk about pluriclosed flow here, but I kind of think of this in terms of sitting in the generalized Ricci flow picture, is you would want to study these pluriclosed solitons on complex surfaces because it could potentially help with understanding this Kodaira classification of complex surfaces. And so in 2018, Jeff has this classification for solitons of the pluriclosed flow on complex surfaces. And if you take a complex surface with a pluriclosed soliton structure, if it's steady, then it's either Kähler or it's biholomorphic to a minimal Hopf surface. And then in this paper, he constructed steady pluriclosed solitons on all of these class 1 Hopf surfaces. And then in 2019, Jeff and Yuri Ustinovsky showed or provided a explicit construction of these pluriclosed steady solitons on diagonal Hopf surfaces that sort of the point of this construction is that it actually demonstrates that they're also generalized Kähler through the construction. And so sort of I guess, big picture idea of what is kind of going on roughly in this setup is these Hopf surfaces, this construction yields sort of like a T2 fibration over like a two-dimensional base manifold, or I guess more generally like an orbifold. And so you have these sort of symmetries where if you think about, you can, from the three-dimensional picture in this 2018 paper, you can kind of like by hands construct from a three-dimensional like Sasaki manifold, which I won't go into the details of here, but you can kind of take like this three manifold structure with like a certain symmetry and then take a product with a line to make like a four-dimensional manifold and then actually build this pluriclosed soliton on it. But with this, we have like two sort of symmetry directions here that if you quotient out by like this group action, what you should get at the base is a two-dimensional orbifold. And you just naturally have the question, like, what do these base manifolds have to look like in dimension 2? But in dimension 2, we don't have any three forms. So you can't really do generalized Ricci flow on it. So what we are going to consider instead is the Ricci-Yang-Mills flow, which Jeff also worked on in his, I guess this is from his PhD thesis in 2007, where we have a Riemannian manifold, and then we consider a U1 bundle with connection A and then curvature 2 form F. And here, the curvature 2 form, basically for everything for the rest of this talk, we're just going to think about all of these things living on the base manifold. So I'm not really ever going to work with like the bundle structure itself. But we get these evolution equations, and these basically look very similar to the generalized Ricci flow equations. And we get steady gradient Ricci-Yang-Mills solitons that satisfy basically the same equations from the generalized Ricci flow setting, but now with a 2 form, which we can use on this two-dimensional base manifold. So we just want to answer, like, what kinds of Ricci-Yang-Mills solitons can we find on these base manifolds potentially? And kind of the natural starting point is, other than just the trivial solitons, are to, like, the first thing that you would think to construct is, what if we just try and find the rotationally symmetric ones? So we do sort of like this rotational symmetry onstats and then try and build them from there. So before we go into the actual construction, though, I'll just talk a little bit about like what is the classification in the classical setting for Ricci flow, say. So if we have a complete steady gradient Ricci soliton on a surface, it's either trivial, so it's just flat, or you have this thing called the Hamilton cigar, which will actually show up in this classification that I will talk about later. And sort of the key tools for these classification results is that on a surface, you have this gradient vector field, grad F, that on the surface, there's sort of the standard complex structure. And if you take J grad F, you get a killing field from the Ricci-Soliton equations. And then if you have a critical point, this killing field by a result of Chen, Liu, and Tian tells you that if you have a fixed point for this killing field, that automatically forces rotational symmetry for your manifold. So there's a bunch of soliton identities that you can get from the Ricci-Soliton equation, taking divergence and trace and Bianchi identities, rearranging things. But this is one of the key identities, which is the gradient of the scalar curvature is equal to scalar curvature times grad F. And this actually tells you that the scalar curvature has to be a constant times e to the f. And in particular, that tells you that the scalar curvature has to have a sign. So that's a very rigid condition on these the types of solitons that you can get on surfaces. And then you can do a maximum principal argument for these non-compact ones to force a critical point for F, which is how you yield the Hamilton cigar. So this Hamilton cigar, briefly, is a rotationally symmetric metric on R2 that was first constructed by Hamilton in the 1980s. That is the unique non-trivial complete steady gradient Ricci-Soliton on a surface. So this is kind of like the one special guy that we have in the surface case. It's asymptotically cylindrical, which you can basically just see from this sort of polar form for the metric. And the way that you could construct this is just by assuming like a rotational symmetry on slots, like dr squared plus phi of r, like phi squared of r, d theta squared, plugging it into the Ricci-Soliton equations, and then doing some basically ODE analysis to solve for what phi has to be. And I'll talk a little bit more about this later, because this is basically what we assume for our construction in the Ricci-Yang-Mills setting. But you can construct this Hamilton cigar. And then sort of the interesting thing is this is the unique one, the unique non-trivial one in the surface case. So that's kind of the context from the generalized Ricci flow setting, why you would consider this Ricci-Yang-Mills flow, and then also like what happens for the classical setting for just the Ricci flow, the Ricci solitons on surfaces. So now we'll talk about this new result. So first part of this is just the existence of a one parameter family of rotationally symmetric steady gradient Ricci-Yang-Mills solitons on surfaces. And it's parameterized by this parameter lambda, which is in the interval -2 to infinity. And I'll say something about why this is the interval that we're considering, but this interval is the maximal interval for lambda. So this is everything. And some special features of the family is that as lambda goes to this -2 endpoint, then the family will converge in the pointed Cheeger-Gromov sense to this Hamilton cigar. And then as lambda goes to 0, you will converge in the pointed Cheeger-Gromov sense to this thing called the cusp soliton, which I'll sort of explain more on the next slide. Then you have this sort of critical threshold at 0, or once you pass 0, so in -2 to 0, you have non-compact solutions. And then once you go above 0, you now have compact solutions. And as you take lambda to go to infinity, after some rescaling that I'll discuss later, you'll actually get S2 with the round metric in that limit. So this is interesting because we've now taken sort of the unique Ricci-Soliton, steady Ricci-Soliton on a surface, and we have this one parameter family connecting it to actually the round sphere. So a couple things to mention. This is like a schematic of what these warping functions are going to look like these profile functions of what these solitons will look like. So this is sort of the radial direction, and then you can think about you just rotate these around, and that should basically just be what these are. when lambda is equal to -2, we have the cigar, and then the region between -2 to 0, we have these non-compact guys that are asymptotic to cylinders. And the radius is actually going to be determined by this constant lambda. And this constant lambda actually ends up being basically just like a Ricci-Soliton identity constant. So then as lambda goes to 0, we get this cusp. So as r is going to infinity, sort of like the circle fiber direction is going to 0. And then once lambda is greater than 0, you start closing off at a finite radius. And so you're no longer getting smooth solutions, you're getting orbifold solutions. And in this construction, I believe these are like teardrop orbifolds. But then as you go to infinity, you get, in this schematic, I drew a circle here, but really it sort of is like you're closing off closer and closer to r is equal to 0. And then you have to do this like rescaling to recover the actual round metric on the sphere. But this is kind of the schematic. So as you dial up this lambda, then, which there's like a nice geometric interpretation of what dialing up this lambda means, you sort of start to close off, and the more you dial lambda up, the faster you close off. So that's proving the existence of these guys. And I guess you would kind of expect that there would be some sort of existence result for just plugging in naively like a rotational symmetry ansatz. But then what's particularly interesting is that this ends up being all of them. So any complete steady gradient Ricci-Yang-Mills soliton on a surface with non-trivial bundle curvature, because if you have 0 bundle curvature, then you just reduce to the Ricci flow setting. And yeah, we are just going to consider sort of the non-trivial ones here. They have to be rotationally symmetric, and therefore they have to be some member of the family from the existence theorem up to basically isometry. So in this classification theorem, so something that is kind of interesting to note is we no longer have curvature rigidity. So like these Ricci-Yang-Mills soliton equations don't give you the same curvature rigidity that is exploited for the classification of the Ricci solitons in the classical setting. But it actually ends up being that you don't need anything extra other than just looking at the ODE. You can just prove all of this directly from sort of elementary ODE analysis. So that's kind of interesting. But something to point out is that this Ricci-Soliton identity kind of gives you like a notion of a generalized curvature, and this is constant for these Ricci-Yang-Mills solitons. So this is kind of playing the role of what's giving us like the rigidity. Okay, so yes, the rotationally symmetric guys exist and then also end up being everything. So I'll first talk about the construction of these solitons, and then just kind of go through like the flavor of the ODE analysis, and then talk about how you actually get the classification once you've done this construction. So as I mentioned before, we have this rotational symmetry ansatz. So we kind of just started by assuming you have a critical point at the origin and then see what happens. And since our killing field has a fixed point, we get rotational symmetry. And this lets us write the metric as in sort of like polar coordinates. You have the radial direction, and then you have this warping profile function phi, and then the theta is like the angular direction. And because we're on a surface, the 2 form for the curvature is going to just be some function times the metric, or times the volume form. I guess here this is not actually the volume form, but you can write this like as a function times the volume form. And then the initial conditions that this warping function need to satisfy for this to be a smooth metric at the origin is that phi of 0 has to be 0 and phi prime of 0 have to be 1. That'll show up later, but the idea is just take this form for the metric and for the 2 form and plug it into the Ricci-Yang-Mills soliton equations and see what happens. And the hope is that you will get some maybe system of equations involving like phi, and then the potential function f, the is sort of like this grad f vector field for the gradient soliton, and then some relationship with the two form. So we have these warp product metric formulas for like the curvature of a warped product metric, and the Hessian. And prime here is just denoting that we're taking derivatives with respect to r, because it's sort of this killing field is telling us that we're sort of invariant under like the rotational direction. So you plug all these things in, but first we use this like Yang-Mills part of the Ricci-Soliton equations to find that actually this two form, it's not just some function times the metric, it ends up being some function with the potential function f times the volume form. Excuse me, not the metric, times the volume form. So this now tells us that when we plug like this f squared term and norm f squared term are going to show up in the Ricci-Yang-Mills soliton equations. Now we can sort of represent everything in these equations as like a system of equations in the warping function phi and the potential function f. And this constant eta is going to basically measure like how strong the bundle curvature is. So this eta is kind of like an integration constant from this like Yang-Mills portion of the Ricci-Yang-Mills soliton equation. And you can kind of dial this eta and still get different solutions for the equation. And then the conservation law, so I call this like the Yang-Mills conservation law, but this ties the Yang-Mills density directly to the potential function, which is why you would think that this is going to reduce to like a system of ODEs and f and phi. So now we have all the parts that we need to basically rewrite our Ricci-Yang-Mills soliton equation in terms of the warping function phi and f. And if you plug all these formulas in, and then you split up this equation based off of like the radial part and the angular part, you get these two different equations, which if you multiply this top one by phi, you can subtract the two and get some relationship between like f double prime, it's like this term and this term end up being related by this sort of identity, which actually by just integrating tells you that f prime is going to now be some multiple of phi, for this mu is kind of telling us how these are related. And this is just another integration constant. So there's going to be some like degrees of freedom laying around here that we need to kind of like piece together later. But this is very nice because it tells us that we have these ODEs in phi and f, and we can now sort of decouple them and get ODEs for just f or phi. And then you think maybe we could like solve these explicitly to tie everything down. And the boundary conditions for the warping factor phi, because it has to be a smooth metric at the origin, imply initial conditions for f double prime and f prime. So that will be relevant for the ODE analysis later. But there's kind of like two constants laying around now. There's like the eta that is giving us like the strength of the bundle curvature. And then we have this mu that's telling us how the warping factor and then the derivative or like the gradient of the potential function are coupled. So, right, I guess one thing I'll point out here is we have this, well, if I go back up here, we can get a second order ODE. Actually, what you get really is a third order ODE, I believe, in the in f from these equations, because f prime is a multiple of phi, and so we're taking two derivatives of phi. This is going to give us a third order ODE in f, but then it ends up there's derivatives on all the terms, and you can integrate one of them away, and you get some second order ODE on f. And this equation actually ends up being equivalent to this constant curvature identity that comes from the steady gradient Ricci-Yang-Mills soliton equations. And this is, I guess, sometimes called the Dilatino equation. But from my perspective, I'm just thinking about it as something coming from the Ricci-Yang-Mills soliton equations. So we have this constant lambda that is given by this quantity. And under this rotational ansatz, we can compute what all of these are, where all the derivatives are just with respect to the radial direction. And this ends up being just equivalent to what we would get from the metric. But it gives a better sort of geometric interpretation of like what lambda actually means. It's like lambda is this constant that comes from the Ricci-Engels-Soliton equations. So we rewrite everything and we can derive these decoupled ODEs for F and phi. And for the most part, we'll be looking at just analyzing the ODE for F, but this phi is also it's the ODE for the warping factor. So if you can solve this in some special cases explicitly, it just tells you exactly what the solitons have to look like. So yeah, I've mentioned there was a number of these degrees of freedom sort of lying around. We can shift one that I didn't actually mention originally, but since we're thinking about gradient Ricci-Solitons, the gradient Ricci-Soliton equations are still satisfied if you shift the potential function by a constant. So you have this sort of freedom to shift f by a constant, but we will just spend that degree of freedom by setting our initial conditions for f, or kind of just ease for the ODE analysis, for f to be 0 at 0. And then these two other degrees of freedom are this mu that's coupling the potential function to the warping factor, and then eta that is telling us what the strength of like the bundle curvature is. And then from the soliton equations, you can get just compute from our initial conditions at the origin that lambda has to be given by this quantity. So we now have a relationship between this mu that's coupling the potential function and the warping factor with the bundle curvature. So these two degrees of freedom end up being linked. And this tells us, like, if we want to think about parametrizing this family by lambda, what is the right quantity to think about scaling? Because we have the freedom to sort of, we could potentially think about fixing one of these and scaling the other. And what we will do is end up fixing mu, this coupling between the potential function and phi, by looking at taking a rescaling of these Ricci-Solitons or Ricci-Engels-Solitons. And if you scale the metric by alpha and the two form by square root of alpha, then if you track what happens under this rescaling, you can fix this coupling constant to be just -1. So I'll just point out, like, this rescaling, the Ricci-Engels-Soliton equations are still satisfied under this. So you still get a solution. And so what we're just going to think about doing is, in general, just assuming that mu is -1. So f prime is minus phi. And then in particular, this lambda from the Ricci-Soliton equations is going to be given by eta squared over 2 minus 2. So it must live in this region -2 to infinity. So that's why this is like the maximal range for this parameter lambda. It's because we've done the scaling to fix this mu. And if you do this rescaling, the ODE for the warping factor turns into this ODE. And I said in the like existence theorem that as we take lambda to go to infinity, we get the round sphere. How this happens is, if you look at the warping factor and you set like alpha to be lambda, and then you take like a sequence of these things going to infinity, then this ODE degenerates to this term goes away and this term goes away, and then this is just like minus phi. So you basically in the limit get phi double prime is minus phi, and then you can say that the solution of that is actually just the round sphere. So then you can do some ODE stuff to show that actually like the family has to converge under this rescaling. But this is how you recover the round sphere, is just directly looking at this rescaled ODE for the warping factor. So there are like these distinguished solutions that I was talking about. So in the limit as lambda goes to infinity, we get the round sphere. At lambda is equal to 2, we just set eta to be 0, which tells you the bundle curvature is 0. And in this setting, you'd actually expect to get the Hamilton cigar because your equations should just reduce to the Ricci solid steady Ricci soliton equations on a surface. And so you recover the Hamilton cigar there explicitly by just solving these things. So this is the warping function that you get that I mentioned on the cigar soliton slide. And the lambda is equal to 0 solution. This is this cusp soliton. This is where you're transitioning from non-compact solutions to compact solutions. And you can also actually just solve this explicitly. So the potential function f has this form, log 1 over r squared plus 2. And then this tells you what the warping factor is. So you can see the warping factor decays like 1 over r. And this gives you sort of the cusp that's developing at infinity, but it's still a complete non-compact metric. So these are kind of the two explicit solutions that you can solve for, and then everything is kind of implicit via the construction. Cool. So I guess I'll talk a little bit about sort of these ODE arguments for both the compact and non-compact case. I won't, I think, go into too much detail with the actual ODE analysis, but the first thing shows, so if lambda is positive, we want to show that we just have these compact solutions. And so when lambda is positive, you have to show that f prime returns to 0 in finite time. And since the warping factor is minus f prime, then that tells you that this metric is basically closing up. One thing that I'll point out is that from the ODE analysis, you don't actually know what like the derivative on phi is as it closes up, but you can basically do some kind of argument to say that it has to be from this picture up here. For it to be a sphere, I believe the derivative at this sort of point where it closes up, the derivative has to be, I think, -1. And so here it's like the derivative is 0, and you can think about these are like sort of interpolating from 0 to -1. And so they're actually closing up like these teardrop orbifolds, basically. But yes, basically the argument goes something like, we have our initial data fixed by initial conditions on the warping factor phi. And initially, you can basically just see that f has to be negative and f prime have to be negative. And you want to show that f prime has to return to 0. But if it does not return to 0, you're sort of in the setting where f is negative and the derivative is negative. So f is going to become increasingly negative. And the structure of this ODE for f is showing you that everything is basically positive here, except for this exponential term that I'll point out is coming from the Yang-Mills density. So the Yang-Mills density is kind of giving us the restoring force here that makes everything work. But as f becomes more and more negative, this should basically go away. And then you would think, okay, if f becomes more and more negative, then eventually these terms are going to, these are always positive. This is going to force f double prime to be positive, and it's going to force f prime back to 0. And then you can show that it can't be uniformly bounded away from 0, because if that ever happens, then since f prime is negative, you can just assume that f grid's arbitrarily negative. This must go away eventually. And if it stays away from 0, then basically after some point, the second derivative is always positive, which contradicts the fact that f prime couldn't be returning to 0. And then that tells you that somehow f prime has to be negative, but can become arbitrarily small. And you can do some sort of argument to show that there's like a threshold where you have to sort of pass some threshold where eventually f double prime has to be positive. And once you're in this region where f double prime is now always positive, it forces f prime to go to 0 in finite time. So you can show this is like uniformly bounded from below once you cross this threshold. So this gives us like the metric closing up again for some finite r. In the general picture, you would expect these so-called orbifolds football orbifolds that look kind of like this. But because of our sort of setup, we're assuming that we sort of are like a sphere at the start, and then they have to close up with a point at this closing out point. So that's kind of the compact case. And then the non-compact case is if lambda is negative, then I guess to show the ODE again, in this case, F double prime, the only negative term was this term coming from the Yang-Mills density, and this lambda is giving us like a positive forcing factor to sort of drive F prime back to zero. But if you make lambda negative, you now sort of have like a negative forcing factor that's going to force F double prime or F prime to eventually stay away from zero. And since F prime is staying away from zero, this is how you get the non-compact solutions, but also you can show that they're asymptotically cylindrical. So the way you do this is just by showing that the limit as r goes to infinity of the derivative has to be, in this case, it's like negative the square root of negative lambda, because lambda is negative. And actually, this lambda constant is telling you like the radius of the like cylinder that you're asymptotic to. So yeah, same sort of setup. You can show that you're initially zero, and then because of the structure of the ODE, when this constant lambda is negative, you actually will find F double prime has to be less than zero in this region, and that'll force F prime to basically just monotonically decrease to this limit. And then the question is like, do you actually hit this limit or do you pass it? It turns out that if you do cross it, so you don't have to pass it, but if you do pass it, you either limit to it or you pass it. And then if you do pass it, this equation from the soliton equation is telling you at the crossing that like the F prime term and then the lambda term cancel, and you're just left with this. So you can only decrease through this value. And that also means that you can only sort of cross it once. And then the question is like, does this continue decreasing? But actually, if you cross it once, you'll eventually just increase back to this thing as the limiting value. But then that tells you that away from zero, you have that this warping factor is uniformly bounded away from zero. So you have a non-compact solution that's complete. And in particular, since this is the limiting value, you have it's asymptotically cylindrical. So that's sort of the just ODE analysis. And then the question is, okay, you can construct these guys, but is that everything? And that kind of comes down to, is this rotational symmetry ansatz restrictive at all? So then we can argue, actually, if you think about setting this like sort of setup that we have initially with this gradient vector field, it gives us this killing field, and just choose local coordinates where you have this gradient. You only have two directions. You have grad f, and then you have j grad f. And j grad f is automatically killing. So you would kind of expect, actually, if you set up local coordinates, you can always set up polar coordinates. But because this thing is killing, you can always get sort of the rotational symmetry that you would expect locally by using the fact that this is killing. And that means that you can actually always write your metric in this ansatz locally. But once you have this, all of the other identities just fall naturally into place, and you can rederive this ODE for the potential function f sort of intrinsically rather than assuming the ansatz that you're starting at the origin. And then you think about just following like the flow lines of f, and because it's the gradient flow, these flow lines exist for all time that like the geodesics are defined, and then it ends up being that if grad f is not equal to zero, you can just kind of keep continuing doing this. So you say, okay, we set up this ODE, and then we ask, can we find a point where grad f is zero? So is it possible that grad f is never equal to zero, or does the structure of the ODE actually force us to have a critical point? So it ends up being that you can actually show that the structure of this ODE forces a critical point. And really all you do is you just do some sort of brute force ODE analysis. So I think we kind of thought about trying to do some other tricks, but the thing that ended up working out for me is just literally staring at this long enough and then going, I think I can actually show it just has to have a critical point for some reason. So I'll outline the case for B is positive. So we have this ODE. This is the ODE that we were originally considering with like this eta and lambda coming from like the Ricci-Salton equations and like the Yang-Mills density. But I'm just going to consider just like this plain old ODE where B and A, I don't really know what they mean. They're just some constants. And so there's going to be three cases where we have B is positive. This is the compact guys. This should be like the cusp solution, and then B being less than zero should be the non-compact guys. But the hard case, sort of surprisingly, is when B is positive, but it actually sort of demonstrates pretty clearly how the Yang-Mills density helps us here. So, right, we just look at this ODE, and you can always reflect solutions of these ODEs. Like previously, we had these initial conditions given to us by the warping function at zero having to be smooth, like extend to a smooth metric on R2 in polar coordinates. We're not assuming anything here, so you just get to basically do whatever you want with the initial conditions, or you don't get to do. The initial conditions have to be very general, but you can always assume by reflecting that you can get at the origin f prime has to be less than zero. And from this equation, you can set up what I call the threshold, which is like this value of f that basically it's telling you when this quantity here is going to be positive or negative. And that should do something to sort of counteract this like f prime term. If you ever get below this threshold, then this term is going to be let's see, this term is going to be negative. So you get this like negative sort of restoring force that should help you get back to zero. Or wait. Yeah, you get some negative restoring force that is going to end up balancing with the f prime. And basically you can show that once you're below this threshold, because f prime you assume to be zero or less than zero, you want to show that it reaches zero. Once you get below this threshold, the ODE forces you automatically back to zero in finite time. And so then the trick is, if I start above this threshold, do I somehow get forced below it? And then you go through a bunch of cases and you can basically show like the only case that you can't just sort of argue through easily is what if f is above the threshold? We can always assume that f prime is below zero. So f is sort of decreasing. But can f approach the threshold with f prime going to zero and f double prime going to zero in such a way that we never actually go below the threshold in finite time? And I maybe won't say too much about this asymptotic scenario, but this is definitely like the hardest part of everything in this construction. The idea basically came to be like, you can think about, we're above the threshold and you can partition this threshold into some subintervals depending on some geometric series, and then play around with the ODE and sort of integrate f prime to get like how long it takes to go through each of these subintervals. And this exponential factor actually allows you to find that the distance it takes in R to drop through each of these subintervals actually is going to be bounded by some geometric series. And then that tells you dropping through all of those subintervals if you sum all these up, that's actually going to have to be some finite number. And so then you do actually hit the threshold in some finite time. And that tells you that you've won because then once you hit the threshold, you can just automatically know that you go back to zero in finite time. So this exponential factor actually does, from the Yang-Mills density, does force the critical point for the compact case. And then it's actually much easier to show that it forces a critical point in the other two cases, which you would think is maybe somewhat surprising because the compact case, it has two critical points in some sense. It's like it closes up at 2 points. Um, but yeah, that is the construction or the argument to show the classification. So as we dial up this Yang-Mills density, this is giving us the restoring force. So this is very important for giving this classification without needing any additional structure. Basically, just like this Yang-Mills density is the thing that allows you to just do this ODE analysis argument to classify everything rather than needing some additional structure. Yeah, so that is basically the argument. You get the existence of these guys, and then the Yang-Mills density really is the juice that makes the ODE analysis the thing that allows you to actually get a full classification rather than just an existence result. So, but yeah, that is, I think, everything for me.
Okay. Yeah, thank you. Thanks, Michael. Are there questions? Um, well, yeah, if not, yeah, we can thank Michael again for the nice talk.
Thank you.